Gauge freedom in electromagnetism is an important concept that can sometimes be a little bit difficult to grasp hold of. You often see it referred to as gauge invariance. Gauge invariance means that equations don't change. Gauge freedom means that you have a certain amount of freedom to choose a starting point. So the key concept here is that we're setting a reference point. Let's imagine, just to be clear, that we've got the electric potential, and in electrostatics we write E is equal to, the electric field is equal to minus the gradient of V. Therefore, we could, for instance, create a new potential V prime, which is just equal to the original V plus, let's say, 10 to the 5 volts. So we're raising the potential totally, but the electric field, E prime, which is minus the gradient of V prime, is equal to E, the gradient of V, because the gradient of the number 10 to the 5 is 0. So this is simply saying that for the scalar potential, we have the freedom to set the 0 point. The illustration I like to use for this is seeing birds sitting on power lines. Those power lines will be at tens of thousands or hundreds of thousands of volts relative to the Earth. But because the bird is entirely localized on the power line, all we've done is added 10 to the 5 to the bird's local potential, and it doesn't change anything. The thing that matters, of course, is potential differences. And because the air which lies between the bird and the ground is such a poor conductor, there's no problem at all. Obviously, if the potential difference between the bird and the ground becomes large enough, then you can have what's called dielectric breakdown. And this is, in a different circumstance, what leads to lightning, where the potential of the clouds is so large that it breaks down the air. So I've introduced the concept of freedom in setting the potentials. So in the scalar potential, it's fairly simple to understand. It's just a number that's defined as the 0 point. When we turn to the vector potential, it becomes just a little bit more complex. Now, if we consider a time-independent situation, just for now, so that we dip our toes into the water here, then in a time-independent situation, we can write phi goes to phi plus c, and we can write this, the vector potential A goes to A plus the gradient of any function f, and it really is any function at all, and in this case E will be unchanged. Whoopsie, missed out a couple of letters there, because E is, in electrostatics, equal to minus grad V, and here the magnetic field B is also unchanged, because B is equal to the curl of A, and the curl of the gradient of any function is equal to 0. That's easy enough to find just by multiplying out the equations. Now, when we are time dependent, things become just a little bit more complex. The reason is that when we're time dependent, the vector potential affects E. So in time dependent, we have E is equal to minus the gradient of V minus dA by dt. B remains the same. B is still equal to the curl of A. We still have the freedom to add anything, which is the gradient of any function, to A. So we can have A prime goes to, sorry, not goes to, but is equal to A plus grad F, and we can say that the curl of A prime is identically equal to the curl of A. Now, because A now contributes to E, then we have to make a change. If we're going to do that to A, then phi prime is going to equal phi minus df by dt plus any number c. And in this case, E prime will equal E. We can just work that one through. So if E prime, which is minus, sorry, I've written phi's there. I've been trying to use V because people were being confused by phi. Forgive me if I get confused. So E prime is minus the gradient of V prime minus d by dt of A prime, and that is equal to minus the gradient of V minus d by dt grad F that's coming from this part, v minus df by dt, and the gradient of c is just 0. And then we add in the dA by dt minus dA by dt minus d by dt of grad f. And I've realised that should be a plus because we have grad v prime, and there's a minus here and a minus there, which gives us a plus. At this point, we get minus the gradient of v minus dA by dt. These two terms cancel, and therefore this is equal to E. Okay, so that's just saying that if we introduce some kind of freedom to how we set the 0 of A, in whatever way we choose to do that, we now have to pay attention to the electric potential as well. Now, why do we want to worry about this? Why do we care about all of this? We're going to see in the next video that you end up with wave equations for the potentials if you substitute the potentials into Maxwell's equations. And the wave equations that we end up with, which I will derive in the next video, are as follows. You get del squared v plus d by dt of the divergence of A is equal to minus rho over epsilon naught. That's the scalar potential. And for the vector potential, we end up with del squared A minus epsilon naught mu naught d2a by dt squared minus the gradient of div A minus epsilon naught mu naught the gradient of d phi by dt, and that's equal to minus mu naught j. So I'll derive those in the next video. And if you look at these equations, you see that these are mixed equations. They both each equation contains both A and V. And I've realised I've put a phi where there should be a V. This is a problem in terms of solving for the potentials, because if they are mixed, then it makes it much, much harder. And what we're going to do is we're going to note that because we have a freedom to set the 0 of A, we can make various choices. And in particular, what we're going to do is we're going to use what's known as the gauge freedom. And the gauge freedom is simply the choice of the 0, in effect, for both A and V. And we're going to use that gauge freedom to set the value of div A, the divergence of A. That may seem like a rather arbitrary choice. Why div A? Well, notice that in this equation we have a div A, and in this equation we have a div A. So it's purely a convenience. The choice that we're making is A goes to A plus the gradient of some function, and we're going to do that in such a way that we can set the value of div A to be helpful. In the same way that we set the value of various different units to be helpful in solving physics problems. There are two key ideas. So remember that if A goes to A plus grad f, then div A will go to div A plus del squared of f. So that gives us a way to set the value of div A just by choosing f so that its nabla squared value cancels that out or sets div A to whatever we want. The first one we're going to imagine or understand is the Coulomb gauge. In the Coulomb gauge, we simply say we're going to set div A is equal to 0. Now, if we just look back at our equations up here, and actually just to make this easier, I'm going to outline our equations in red boxes just for a moment. There we go, there's the first one. And that rather long and complicated one is there. Okay, that makes it easier to see. If we set div A equal to 0 in this first equation, let's give these equations numbers, then you can see that equation 1 here becomes much simpler. In fact, it becomes the very familiar electrostatic equation. So equation 1 becomes del squared V is equal to minus rho over epsilon naught. Equation 2 becomes a little simpler, but it's not really much better. So equation 2 is del squared A minus epsilon naught mu naught d2a by dt squared. The minus grad of div A becomes 0, but we're still left with this cross term minus epsilon naught mu naught grad of dv by dt, and that's equal to minus mu naught j. This is often used actually in a time-independent problem. So time independence means that we get rid of, obviously, things which are time-dependent. And what that gives us, independence. It's harder to speak and write different things at the same time than you might think. If you have time independence, then we end up with del squared A is equal to minus mu naught J. And you wouldn't actually have got that without setting div A equal to 0 as well as time independence. So that's where the Coulomb gauge is used. It's typically used in static problems. It makes those equations simpler, but it's not something we're going to use in the general case. In the general case, we're going to use what's known as the Lorentz gauge. And please notice that Lorentz is different to Lorentz. There's a difference of a T and also a nation. So the Lorentz gauge is defined as div A plus epsilon naught mu naught dv by dt is equal to 0. And if we just pop back up to equation 2 here, we might see why this is interesting. I'll write this out in a minute. We've got a div A, we've got a dv by dt. So let's just rewrite our equation for A. If we rewrite our equation for A, then we have the following. We have del squared A minus epsilon naught mu naught d2a by dt squared. And then we have, sorry, I'm just trying to collect terms here in my head. We have a minus, the gradient of div A plus epsilon naught mu naught dv by dt, and that's equal to minus mu naught j. So if we compare that with our equation up here, you'll see that all I've done is to move the gradient here and here, these two gradients outside, and bring these two terms together. You can, of course, now see immediately why the Lorentz gauge is so helpful. If this term in brackets is 0, then we can write a very simple wave equation for A. We have del squared A minus epsilon naught mu naught, though of course let's just remember that epsilon mu naught is 1 over c squared d2a by dt squared is equal to minus mu naught j. So that's a wave equation for A with a source term, which is j. If we use our equation, the Lorentz gauge, to write that the divergence of A is equal to minus epsilon naught mu naught dv by dt, then we can rewrite the equation we had up here, equation 1 for V. And what we find immediately is that del squared V minus 1 over c squared d2v by dt squared is equal to minus rho over epsilon naught. And in both cases, we've used the fact that epsilon naught mu naught is 1 over c squared. These two equations are key. They are the wave equations for the potentials in terms of the charge density and the current density. Notice that they are of very, very similar form. They will be important when we think about relativity, and I will derive them more fully in the next lecture. But this is why we choose the Lorentz gauge, is because it makes the solution of these problems significantly simpler. So to recap, when we talk about gauge freedom, we mean the freedom to choose the zero of the scalar potential V and the vector potential A. Remember, we can add grad f to A, therefore in effect we're able to set the 0, just as we can add any number we want to V. When we talk about gauge invariance, we mean that the magnetic field and the electric field are not affected by our choice of gauge. In the next video, we'll go through these wave equations for the potentials in just a little bit more detail. We'll show where they've come from and discuss the implications that has.